Well, hello, everyone. It's a pleasure to be here presenting about Venus, which is the planet that I have spent basically my entire career, which is yet not that long, but the past, let's say, 5 years working on. And yeah, I hope to give you a nice overview about it. I know EAI has a very broad interest range and expertise. So yeah, I'm trying to give a general overview and also talk about the future missions and what we can expect to find, some of the things we can expect to find with these missions. So let's start. Yes, so let's start actually from the beginning. Venus, actually right now at the night sky is very clear, is a very bright spot, and is actually the third brightest object in the sky. And of course, it was known and studied for centuries. But I'd say that the first most important discovery about Venus came on the 17th century when Galileo observed Venus with a telescope and showed that and found that Venus has phases like the moon, which was let's say one of the pillar proofs that the center of the universe is not the Earth but the sun. And on the 19th century, we knew that Venus was kind of Earth-like, so that we know that the mass and the size and the distance to the sun was about the same of the Earth. So we really thought it was a very much Earth-like planet. And in fact, many scientists and also, of course, many science fiction novelists wrote books about how Venus could have monsters and lakes and forests and dinosaurs and monsters. And actually, this was something that was really considered until the mid-20th century, when the first radio observations of Venus showed that actually the planet has an extremely hot surface. We knew we had an atmosphere, but we didn't know how big this atmosphere was. And we actually found out that the atmosphere of Venus is really, really massive and CO2 dominated, which makes a very hot greenhouse effect. And the surface temperature is actually about 470 degrees Celsius, impossible for any life as we know it to survive. And Venus was actually also the stage of the first successful interplanetary mission, which was the Mariner 2 mission. And then we enter in the phase where we really start discovering a lot about Venus. So this is the first radio observations indicating that Venus is too hot, and then this is Mariner 2. And then we enter in this phase where we have all of these space missions that goes to Venus. And each point here is a mission. When we had a cross, it means that the mission failed. But you can see that from the 60s to the 80s, Venus was one of the main stages for the Cold War, for the exploration of space between the fight between the Soviet Union and the US. And there were a lot of successful missions and a lot of very interesting things we found out. So as I said, Mariner 2 was the first one, and it really confirmed the surface, high surface temperature and pressures. And in 1967, actually, we had the first successful descent capsule through the atmosphere of another planet that showed that Venus has an atmosphere composed of 95% of CO2. Then we also had the first successful lander on another planet that was also Venus. And this was the first direct measurement we had of the surface that shows the surface temperature of 740 Kelvin. And we also had the first photo of the surface on the planet was also on Venus, also by a Venera lander. So this is Venera program, was the Soviet program. And this is the photo. And finally, I'm gonna highlight here this mission called Magellan. This was the last mission that NASA sent to Venus, launched in 1989, and orbited the planet from 1990 to 1994. And he obtained the best data we have to date in terms of the of surface imagery, which is actually done with radio because of the atmosphere. We cannot image the Venus surface as we do for other planets. So we had to do some synthetic aperture radar imaging, also the best altimetry, so best topography information we have, and also best gravity data that we have that tells you something about the interior of the planet. Later on, we only had 2 more missions to Venus. Venus Express, the first and only to date European mission to Venus that was more focused on the atmosphere, and also Akatsuki, also focused on the atmosphere. So most of the data, the images that I'm going to show you today are coming from the Magellan mission. All right, so let's go into it. So this is a global map of Venus, the topography of Venus. So the topography shows where you have highlands and where you have lowlands. And we can see that for Venus, Venus has quite a smooth surface. 80% of the planet has, let's say, a topography on the range of 0 or below 0 kilometers altitude. And we have this kind of sporadic mountains and highlands over the planet. So in these lowlands, this is mostly composed of basaltic plains that has some kind of tectonics, like wrinkle ridges and other types of tectonic features. But the highlands are where you have a lot of interesting stuff. So you have these big, I cannot see my mouse. Anyway, we have this big, this one particularly is called Ofta and is about the size of Australia. It's a big feature that is thought to be formed by tectonic stresses, so built up by, for example, compressive tectonic, probably. And we think from the gravity data as well, we know that they are nearly isostatic compensated, something like iceberg floating on water, or even what we know about the Himalayas. So we have these high mountains and we have these crustal roots, deep crustal roots underneath it. But we also have another type of highlands that are less continent-like, let's say, that are called volcanic rises. And these regions, they from the analysis of the topography and of the gravity data, we think that what we call they are dynamically compensated. So their high topography is mainly caused by the fact that you have a mantle plume, like a hotspot as you have in Hawaii, that managed to push up the surface and generate what we call this dynamic topography. And also these regions are closely linked to volcanoes. So this is a map of all volcanoes larger than 5 kilometers on Venus. If I showed all the volcanoes, you wouldn't see the surface because Venus has over 80,000 volcanoes, mapped by Rebecca Hahn and Byrne. And yeah, so you have these types of rises. They have they're linked to the largest volcano on Venus that can reach over 500-kilometer diameter. And they are spread. Yeah.
Juliet, could you just press hide on your screen? There is a little zoom message and it's blocking the bottom graph.
Okay. Wait.
Perfect.
Okay.
Thank you so much.
Yes. All right. So beyond this many volcanoes, Venus has other very interesting features, and one of the highlights I'd say is this what we call the coronae. So the coronae, Venus has like about 700 of those. These are quasi-circular features that don't really exist in any other planet as we see on Venus. So here on the right, I'm showing the largest one of them. This is called Artemis corona. And we think that this rim that we see here, that form the edge of this 2,000-kilometer large corona, it's might be a signature of pillback of subduction. So you have a mantle plume that came here and managed to burst through the lithosphere and caused some kind of rollback of the lithosphere and lithospheric subduction. And it might be the only terrestrial planet as we have signatures of subduction. So this recycling of the crust and of the lithosphere as we have on the Earth. And sometimes these features are also, as I'm showing here on the left, linked together within rift zones. So this is also very interesting. And as I said, they are spread all over the planet, and their formation mechanisms probably vary a little bit from one the other. And this is also a big topic of research on Venus as well. Another point I want to bring in is about the surface composition. So we know very little about it because we didn't have a lot of in situ measurements, and we cannot really do spectroscopy of mapping as we do for Mercury and Mars and the Moon because of the atmosphere. But we have these direct measurements of major element compositions from the Venera lander, and what we see is that they are very similar to mid-ocean ridge basalts on the Earth. So we kind of expect Venus to be mostly a basaltic planet full of volcanoes and so on. Okay, then I'm gonna bring maybe the most surprising, perhaps the most surprising finding of the Magellan, which was the distribution of impact craters. So as you know, in planetary sciences, the way that we do to map the age of a surface is counting the craters and seeing how they vary from one terrain to the other. And what we found for Venus is that Venus has about 1,000 craters, so that's quite few in comparison to other planets like Mars and the Moon. And this indicates an average age of 250 million years, which is relatively young also compared to these other planets, and about the same age of old oceanic crust on the Earth. And and maybe more interesting than that is that we cannot see a difference in age. At least from statistics, it's impossible to distinguish their distribution from random from one place to the other, which kind of indicates that the whole surface has about the same age, which is also quite surprising in terms of geology. Like, how can you have the entire surface that is basically about the same age? There's also no major impact basins, and so the largest one is Mead, which is 275 kilometers. And you also have very few small craters, but this is expected because of the atmosphere, because the atmosphere kind of destroys all the small stuff. And another interesting point is that, and this is a bit debated, is about how many craters on Venus are in the stage of modification, so they are being eroded or erased. And it seems like only 10% of them are in this kind of intermediate stage, but this is also a little bit debated. And because of this crater distribution, this very unique crater distribution, there was two ideas that appear to explain the resurfacing history of Venus. I'd say that the one that dominated after the Magellan mission was what we call catastrophic resurfacing hypothesis, in which they understood that because we have this kind of uniform age, there was probably a major geological event about 250 or 500 million years ago that completely, entirely resurfaced the planet in a kind of almost geologically instantaneous manner and created a clean slate for new craters to come. And this major event could have been kind of super intensive volcanism everywhere, or some kind of global recycling event. So kind of we have intensive plate tectonics for a short period of time, and then this stopped. And then today we would have a very quiet, quiescent, geologically almost dead planet. And then there was a second hypothesis that I would say is growing a little bit in the past decade, which is the equilibrium resurfacing hypothesis. The idea here is that instead of having this instantaneous event, you actually have geological activity in the same rate and the same spatial distribution as you have crater creation. So you have this continuous formation and destruction of craters, and you have a planet that is consistent with being more geologically active today. And this actually had some implications of how do we understand the long-term evolution of Venus and the planet's interior dynamic and how these dynamics evolved over time. So for Venus, we know there is no plate tectonics. There's no clear plate boundaries or these kind of lineaments of mountain ranges and volcanoes as we see on the Earth. So it's clear there is no plate tectonics. So we can kind of cut this first model here. But we are actually still unsure what is the main regime that rules Venus geodynamics and leads the planet to lose its internal heat, right? Because it's a big planet, there's a lot of heat trapped in it, and it has to lose this heat somehow. And then from linking the geology, this resurfacing hypothesis and what we've seen on the surface, there were a few ideas that came out. So, of course, there's a possibility that Venus it's more or less a stagnant lid, like Mars and the Moon and Mercury, in which you have this lithosphere that is pretty much stagnant. Nothing has happened much over its it hasn't moved. There's no real lateral movement in the lithosphere throughout the evolution, and most of the heat is sought through volcanism and also heat conduction through the lithosphere. There's a second idea that came, which is called episodic lid, that is very much linked to this catastrophic resurfacing scenario, in which because Venus is a big planet and has a lot of internal heat, just having stagnant lid is not enough to release all the heat coming from the planet. So at some point, the planet's so hot that it kind of causes some thermal instabilities that will generate an episodic case of, let's say, something like plate tectonics that is going to restructure the entire planet, and then it's going to go quiet again for some time, and then this cycle will repeat itself over time. And then finally, there's a new idea called plutonic squishy lid, in which the planet, it's mostly you have magmatism, so you have melt being formed in the interior, but instead of being put on top of the surface as volcanism, most of the melt is trapped within the lithosphere. And this will cause some kind of local scale lithospheric dripping. I'm going to show this a little bit later. So as I said, there's this episodic lid scenario that is this change in tectonic regime that could be in line with the catastrophic resurfacing case, and this would mean that today Venus would be in a very quiet stage, geological, like not much happening in terms of geological activity. Then we have this stagnant lid / heat pipe. Heat pipe is this idea that actually came from studying Io, that you have a lot of melt, a lot of magma being produced in the interior because there's a lot of heat in the interior, and all this melt is put on the surface as extrusive magmatism, and this ends up creating this thick crust and very stagnant crust and lithosphere, which could be also a scenario for Venus, because Venus models suggest that it still has a lot of melt being generated at present day. And of course, you have this constant volcanism. This could be in line with an equilibrium resurfacing scenario. And then we have this third plutonic squishy lid regime, in which you, instead of putting the melt directly on the surface, so on this scheme here on the right, you have extrusive magmatism, which is kind of this heat pipe scenario. So all the melt you generate in the mantle is put directly on the surface, while in the plutonic squishy lid phase, you can put most of the melt instead within, typically in the base of the crust. And because you have this hot material heating up the lithosphere, the lithosphere starts getting weaker and weaker, and this will allow you some dripping and some delamination. So potentially some crustal recycling and lithospheric recycling at a more regional scale. So it's another way to recycle the lithosphere in another scale, and probably in a more global and random way, kind of similar perhaps with equilibrium resurfacing hypothesis. So one study that we did that came out last year was to compare when we have only extrusive magmatism, so this heat pipe scenario, and when we have a highly intrusive magmatism case. So we did 3D geodynamic modeling of Venus, and then we compared them. So from that, we estimated the thermal gradient. So what would be the temperature of the lithosphere at present day? So we let the model evolve for about 4.5 billion of years. And we see at present day what is the thermal gradient of the lithosphere. And we compared that to what we observed from some geophysical constraints that I'm not going to enter into here, but we can constrain the temperature structure of the lithosphere from from some geophysical analysis of the topography and of the gravity data. So here on this right plot, we compiled all these estimates that have been done in the past, and we compared them with the predicted thermogradient from only extrusive magmatism and when you have a lot of intrusions. And what we can see is that when you only have a lot of extrusive magmatism, because you put this melt all the way to the surface and it cools instantaneously to the surface temperature, and you kind of create a more and more thick cold layer of the crust of this material, you end up with a very, very cold lithosphere that is very much inconsistent with what we observe in terms of constraints for the thermogradient from data. But when you have a lot of intrusions, you can see here these bright yellow spots here. This melt pockets allows you to locally really very much increase the temperature of the lithosphere there. And this starts being very much consistent of what we see in some points on the Venus lithosphere, that you can have very high thermogradients. So from just this analysis, we can already help ruling out a extrusive magmatism scenario, and also see that this intrusive magmatism, the squishily proposed regime, seems to be consistent with the observational constraints for thermogradient at least. And so what ends up with, what about the episodic lid regime? So for this, we cannot, so for this study, we didn't really went into the episodic lid case. But one thing that to understand it, to differentiate episodic lid from the squishy lid regime is to have very good constraints on how active is Venus today in terms of geological activity, right? And we don't really have that constraint very well set today, but we have, in the past decade, I would say, more and more indications that Venus is more active than what we previously thought. So thinking that Venus today is a completely dead planet, I think is an idea that everybody, I hope most people agree, is probably not the case. But how active it is, and if it's enough to have this kind of platonic squishy, we still don't know. So here, just to show you a few examples of findings from the past years that shows that this potential activity. So first, from Venus Express data, this study by Emmanuel Macaro showed that you had these temporal variations of SO2 at the cloud top, around the cloud layer region, which could be associated with outgassing from volcanoes. So we have volcanic outgassings that generate some kind of instability in the atmosphere that generates this temporal variation of SO2. There's some ideas that also say that this might be just some kind of normal process of the atmosphere itself. I'm not especially on it, but yeah, this is not, let's say, not 100% indication, but it's a nice result. And then we had this study by Smerker et al. In 2010 that showed there's this correlation between what they see from a surface emissivity. So Venus Express also observed on the southern hemisphere, they did some surface emissivity measurements, around the 1 micron band. And they saw that on top of a few volcanoes that seems to be quite young, there is also this high emissivity anomaly that indicates that there might be some unweathered basalts here. So this might be an indication of a fresh lava flow. How fresh it is, it's still, let's say, debated because we don't really know weathering rates on Venus. But people say from hundreds of thousands of years to even years. But this is, I'd say, still a bit open. And finally, and I think the strongest observation that we haven't had until now is the direct observation with synthetic aperture data from the Magellan. So Herrick and Hensley, they compared images from the Magellan data from 2 different cycles that were, I think, 1 or 2 years apart. And what they saw of the same region, and what they saw, I think the main observation was that this change in this vent. So it seems that one vent expanded, and potentially there's also a new flow that appeared. And was a very, very nice result. And I'd say it was the first direct evidence of volcanic activity on any other terrestrial planets besides the Earth ongoing today. Okay, so this is the present day activity on Venus, but we really don't know much about the past of Venus since the surface is so young. But there are some regions on Venus that might be analogous to continents, that might be some kind of fingerprints of earlier on the planet evolution, and they might tell us about how Venus was in the past. And these regions are called tessera plateaus or crustal plateaus. They have a few different names. And these are these highlands that I said that are associated with these crustal roots, which is more or less, in terms of interior structures, more or less similar to continents on the Earth. These regions, they are associated with highly tectonized terrains that they call tessera on Venus. And tessera are basically defined by is a terrain that has different directions of tectonization. So you have, as you can see in this panels here, you have really, really complex deformed terrains. And I think another key observation from one of these crustal plateaus that I'm showing here on the right was, again, this emissivity, 1 micron emissivity measurements by Venus Express that showed that at this plateau called Alpha Regio, it is associated with a low emissivity anomaly. And let's say one of the best ways to explain that is by it's because the iron content is low. So this could be a very strong indication that these terrains are actually made of felsic rocks instead of basaltic rocks. So felsic rocks is also what forms continents on the Earth, and they are always associated with some kind of remelting or recycling and remelting of basaltic material at greater depths that then that are remelted and then brought back to the surface as this granitic, so felsic, silica-rich materials like granites. And this was another interesting evidence that Venus could have this kind of crustal recycling. But more than that, we know that on the Earth, these felsic terrains, they are associated with water. So this was also the one idea that came, is that if Venus has felsic rocks, it might mean that it also could have had water in the past. Okay, so one thing that I did was to investigate the interior structure of these regions to try to estimate what are their crustal thickness, and also what is the lithospheric thickness in these regions. And I'm not going to enter in a lot of detail into this, but we do some modeling of the interior structure, assuming that the lithosphere behaves as an elastic shell and so on. And when you place a load on top of this elastic shell, the shell will deform. And the amount of deformation, so the amount of bending that the lithosphere will go through, is associated with the thickness of this shell. So the thicker it is, the less bending will do, and the larger the gravity signature will be. And this is shown in these panels on the right. And when you have a more thinner shell and weaker lithosphere, you have this closer to, if you know the term area isostasy regime, where you have a much smaller gravity signatures. And this tells us about the thermal conditions during the formation of these regions and so on. So it tells you about the interior structure. And what we were able to do was actually constrain the crustal thickness of these regions. And we saw that on average, the crustal thickness is about 30 kilometers, but at certain depths, they can reach depths of over 40 to 50 kilometers. And the idea that we had is that if the roots are deep enough and really go through this 50-kilometer depth, it could be that these basaltic roots could remelt and form these felsic rocks. And that's what we, with a petrologist that knows all about this melting and phase transitions of rocks, that did this modeling, Max Collinet, and we collaborated on this to try to understand if you could form these felsic rocks by remelting the crust. So let's go through this plot a little bit slowly because it's a lot going on. So here you have pressure and temperature. You have an initial basaltic composition that is similar to the Vega 2 measurements from a Soviet lander. And we see what happens to this, the phase transition. So what happens to the minerals of this basalt as they increase temperature and pressure. So the metamorphic compositions. And what happens is that at some point you start forming garnet, and you start destroying feldspar and forming garnet. And what happens when you start forming garnet is that the density of your rock start increasing and increasing more and more. So what I show here we show here in the background is the difference in density between the crustal materials and the mantle materials. So as you start having more and more of garnet, your density of the crust increase more and more, and at some point it can go over the density of the mantle itself. And that is interesting because then you start having a negatively buoyant material that can just what they call delaminate. So they could drip off the crust and go to larger depths and have some kind of crustal recycling that way. And on top of that, at some point you start having quartz entering in your system. And what does it mean is that you start having melts that are more silica rich and potentially more felsic if this rock you ever end up melting it. That's what we're gonna take a look now. So this line here I don't have my mouse, but this almost vertical line here is the solidus line, which shows when you start melting the rock. So the more you go to higher temperatures, the more melt volumes of partial melt you have. And here, what we're showing is the composition of, so the content of SiO2, so the amount of silicate, which kind of tell you how felsic the rock is, at 5% melt fraction, and on the bottom at 25% melt fraction. And I'm going to focus here on the 25% case because if you want to form an entire crustal plateau that is felsic, you really need a lot of melt. So we're not interested in this low melt fractions. So we have one curve for Venera 13, and this is kind of a special case. Venera 13 has a weird composition, and so I'm going to ignore this at this point. But if you look at the Vega 2 and the Venera 14 cases, what we see is that as you start increasing the depth in which you melt, you actually start adding this quartz into your composition. Your silica content increases from 50 to 60 to over 60%, which you start being intermediate to felsic rocks. And this is just melting dry basalt with no water whatsoever. If you add a little bit of water, so 1% of water to the system, the composition doesn't change much. What happens is that you start having this felsic composition a bit shallower. So it's easier to make such compositions, but it's not, let's say, not mandatory to create these felsic melts. So just from petrological analysis, having felsic melts does not necessarily mean that you needed to have water to form these rocks under Venus conditions. Another question is if you can migrate dry felsic melts, because they are very viscous and maybe that's not possible and it's something else to look into. But just from this, you might not necessarily need Venus to have water in the past if we find felsic rocks indeed. And this is just two scenarios that we have to form them. Let me check the time. Okay, we have some time. So one is this case where you have this thick crustal roots that we really can have from this geophysical analysis. And this could, if you bring them deep enough, they could have this quartz formation and also melting, which would allow for the formation of felsic melts. And these roots that are very dense because of all the garnet and so on could potentially delaminate. Another idea is that if you really have this kind of local subduction, and as we've potentially seen some corona and that are kind of predicted by this plutonic squishy scenario, you could have also this formation of felsic melts just by recycling the crust. But we still end up, after all of this, with these big questions are not yet solved, right? So what are the geological processes that make the surface of Venus so young? We still don't know. We're still in this episodically versus some kind of perhaps Platonic squishy debate. And what are the properties that cause Venus and the Earth that are about the same size and density? So they probably originally has about the same composition. How and at what point they evolved so differently? And what did early Venus look like? If we have felsic melts, does this really mean that we had water? Like, are there any indications that Venus was more Earth-like in the past and only changed more recently? All of these are still open questions. And I think these are very important questions that help us understand how you form habitable worlds like the Earth, or worlds with plate tectonics and all of that. And because we have these big questions, actually in 2021, we had 3 new missions of Venus accepted. Da Vinci and Veritas are 2 NASA missions, Discovery class missions. The Da Vinci probe, it's the main part of the mission will be an entry probe that will measure the properties, the chemistry and physical properties of the atmosphere, and also imaging parts, a part of a crustal plateau. Then we have Veritas, which is an orbiter that, it's going to measure. I'm going to talk more about these 2 later. So Da Vinci, I'm not really involved in, but Veritas and Envision, yes, and they are more focused on the geology of Venus. Okay, so just to tell you a little bit about what Veritas will do, they have a synthetic aperture radar that's going to do a global new global coverage with radar images at about 30-meter resolution, and also a new global topography map at a 250-meter horizontal resolution. And this is just to show you how improved the topography will be. So this is the current state of Venus topography resolution that we have, which is about 2 kilometers, which is kind of, this is just an example showing the San Andreas Fault. And this is what we would see of Earth if we had the topography resolution that we had for Venus. So very little, you can barely see any faults, you can barely see what's going on. And this is what we're going to obtain with the new global topography map. So it's going to be a huge difference, and we're really going to learn a lot about the geology of the planet from that. And I think another very interesting thing we're going to have is the repeat pass interferometry, which for a handful or maybe 2 handfuls, about 12 locations, we're going to be able to see centimeter changes from one cycle to the other, which will be very interesting to look for geologic activity, volcanic activity, and so on. Envision is a more, let's say, holistic mission in the sense that it's going to observe from the atmosphere, upper atmosphere, down to the core. So they're going to have 3 different spectrometers, 2 focus on the atmosphere. 1 is also this focus on this emissivity from the surface to have some more information about these felsic rocks and so on. Also a radar, but this is going to be targeted instead of global, and also a subsurface sounder, and also new gravity data. Veritas is also going to give some new gravity data. And one of the big questions, actually, these 2 missions are going to answer, is to give this global map of composition from emissivity measurements. So from Venus Express, we were only able to get this for 1 region, and it was just, I think, 1 or 2 bands. And with the new instruments that is actually being built at DLR, where I was a postdoc until last month, we're going to have much more information and be able to tell with much more detail the kind of this felsic to basaltic transition. And this kind of global composition map is going to be super interesting for us to understand how felsic these are, so how continental-like they are, and what formation mechanisms could we use to explain these compositions. Another interesting thing is the gravity data that's going to improve a lot, and it's going to really let us do another level of interior structure investigations of these regions. And one example is exactly about the crustal plateau. So from the data that we have now, the resolution is so low. So the spatial resolution is going to improve from about 200 kilometers, that what we have now, to about 100. So at least going to double. And this is going to make a huge difference in what we can tell about the interior structure. Because if we assume with this new data, we actually, one key thing we're going to be able to see, I think, is the change, is variations in density of the crust. So with the data we have right now, we cannot tell anything about crustal density. And crustal density is closely related to composition. So if indeed we are able to constrain that these crustal plateaus have a lower density than the surrounding regions, which I think we will be able to do, this is also going to tell us a lot if these regions are indeed like the continents on the Earth or not. And this is going to be very important to understand the evolution of the planet. So in summary, the geodynamic regime of Venus is still largely debated. We still don't really know if the planet had phases of intense surface mobilization and is currently in a more quiet period, or if in fact the planet is more consistently having this continuous but small scale recycling of the crust and geological activity in general. And this was, and we will be able to learn more about this with the new missions by having more direct measurements of current geological activity, and also we're going to improve heat flow estimates and understanding better the interior structure. It's going to help us a lot on that front. And also we have to understand one of the key ingredients to understanding the past of Venus might be these crustal plateaus that could have this continent-like composition, so felsic composition, which would provide a strong evidence for crustal recycling, because we really need to remelt crustal basaltic rocks at large depths to obtain that. But it might not indicate that it had liquid water, and that's something that should be further investigated. And having a global map of these compositions would really help us understand all these ideas of how they could have formed. And that's it. Thank you very much. Just a last minute self-promotion that we just, with Maxence Lefebvre, we wrote a very small paper on this current state of knowledge on Venus, if you're interested in it. And it's short and sweet, and there's like a lot of references. So if you want to learn more, just go check it. Thank you very much.
Yeah, I have a question, because you didn't talk at all about the degassing of all the volcanism on Venus and how it might impact. I was wondering, for example, potential recycling of the crust, the basaltic crust at some point. I was wondering if you had any idea on this.
It's a very interesting question. I would say that this degassing and coupling interior atmosphere is not my main expertise, but I'd say that it is an extremely complicated thing to do, to couple like the full thermoevolution modeling with melting and outgassing. But people are working on it. I would say that people started working on it about 10 years ago. So Cedric Gilman is one of the main people doing that. And what we know is that it definitely has a major impact. So as you start melting more and more, you start degassing, and this is going to generate a thick atmosphere. This is going to increase the temperature. And when you change the surface temperature, you change the rheology of the lithosphere, right? So everything starts being a little bit more ductile, and it's harder to break the rocks at higher temperatures. And it's going to have an impact on how you can recycle the rocks. And yeah, so there's kind of this feedback mechanism for sure. And I'd say there's still quite a big way to go in terms of understanding this full coupling between the geodynamics and the atmosphere, but it is indeed super important, and it's something that we really need to improve to fully understand the evolution of Venus. And also talking about magma ocean phase, the formation of the early atmosphere, I'd say it's also something that is debated, that if you form this super thick atmosphere very early on, just after during the magma ocean, or if you had a shorter magma ocean that had a more mild atmosphere and you only have this major buildup much later on. This is another idea that I'd say still very much debated, and unclear, but it's a very nice point.